Flow over a circular cylinder is a long-studied problem for its many applications in the real world. In the early days of rocketry, Konstantin Tsiolkovsky worked on cylinders in the first-ever Russian wind tunnel, developing early methodologies for testing. Though most of his findings went unrecognized by the Russian government, they have gone a long way towards analyzing the flow effects over blunt bodies. Smokestacks, chimneys, and light posts, among many other objects, experience similar aerodynamic effects due to their cylindrical shapes. Simple experiments such as the one our group conducted in Cal Poly's low-speed wind tunnel can yield valuable insights into the complicated flow patterns. These flow patterns are dictated by Reynolds number, which is a function of velocity and environmental conditions. Cylinder flow can be divided into 4 distinct regimes, which dictate how vortices form and where separation occurs on the cylinder. The separation point on a cylinder can be described simply as the point at which flow detaches from the cylinder. This detachment is caused by an adverse pressure gradient in which the velocity of fluid particles near or at the surface reaches zero. Past this separation point, a wake is formed where vortices are generated and shed. This occurs at a frequency determined by the Struve-Hall equation, which allows for estimation of shedding rates based on flow velocity. The wake and vortex shedding increase pressure drag on the cylinder, which is the dominant force on any blunt object. The highest point of pressure, called the stagnation pressure, occurs at the point furthest upstream. At the stagnation pressure point, the coefficient of pressure is equal to 1. Pressure coefficients along the surface vary and are calculated by using the Bernoulli equation, which can then be used to show high or low pressure points. The theoretical and viscid coefficient of pressure values should be equal to the function 1 minus 4 sine squared theta.
The objective for this lab consisted of gathering pressure data within the laminar vortex regime at various Reynolds numbers. At the same time, flow visualizations were recorded to observe flow separation and vortex shedding. The pressure data is used to calculate coefficient of pressure around the cylinder and to calculate pressure drag across the surface of the cylinder. The flow visuals are used to observe the weight characteristics and the shedding frequency. In addition, runs are completed with and without a trip strip to allow comparisons between tripped and untripped pressure, drag, and vortex generation for different Reynolds numbers. For our experiment, we used the Cal Poly low-speed wind tunnel, which allows for precise measurement and visualization of flow fields up to 58 meters per second. The wind tunnel is equipped with a Scanivalve 64-port pressure measurement system, of which 24 ports were hooked up at 15-degree intervals around the circumference of our 12.06 centimeter diameter test cylinder. The atmospheric temperature during the experiment was 21.0 degrees Celsius, with the corresponding pressure of 1013.1 hectopascals. This led to a calculated density of 1.2001 kilograms per meter cubed. The cylinder itself was fixed in the center of the wind tunnel test section, midway between ceiling and floor, as shown. To better visualize flow, a smoke machine was used at the test section inlet to better indicate turbulence and vortex shedding downstream of the cylinder. This was accompanied by a green laser array that illuminates the smoke and blackout curtains that prevent obscuration by ambient sunlight.
Here we see, in slow motion, how the flow interacts with a cylinder at a Reynolds number of 2.56 times 10 to the fourth. The laser provides some insight into how the smoke is moving. However, since the experiment was performed in the middle of the day, the insight was limited. Another angle reveals how the vortices are generated behind the cylinder. The flow looks laminar as it wraps around the cylinder before becoming turbulent in the vortices. The vortices then clearly spiral as they travel downstream from the cylinder. This is exactly what is expected from flow at the given Reynolds number. Plotting pressure coefficients against angle from the leading edge allows for comparison to the theoretical invested values. Our data closely matches the theoretical until flow separates at about 50 to 60 degrees. This is also visually represented in the plot of pressure overlaid on a unit cylinder. The highest pressure is seen on the leading edge before tapering off and separating. The stagnation pressure is notably less than the vacuum pressure seen behind the cylinder. Now looking at the flow with a Reynolds number of 5.75 times 10 to the fourth, we still see laminar smoke around the cylinder. However, the vortices are clearly much more frequent and turbulent. A freeze frame reveals several distinct vortices.
Our coefficient of pressure plot reveals the same deviation from inviscid theory as before. Again, flow separates, creating a high magnitude low pressure zone behind the cylinder.
Here we compare the calculated coefficient of pressure values at both 100 RPM, seen in blue, and 200 RPM, seen in green. The inviscid theoretical values, seen in red, are plotted again for comparison. The most notable differences between the coefficients of pressure for 100 RPM and 200 RPM fan speeds is that at a higher RPM/Reynolds number, the flow separates earlier. This can be seen as the green line deviates from the red a little earlier than does the blue. The second important thing to note is that once the flow has separated, its laminar flat line sits higher at higher Reynolds numbers. This comes largely from the fact that the coefficient of pressure is inversely proportional to velocity, and as velocity increases, the coefficient of pressure magnitude will slightly decrease.
Having laid the trip strip, we now run the tunnel again to produce the same Reynolds number of 5.75 times 10 to the fourth. At high speed, it is difficult to notice any difference in flow. At this angle, and with better laser utilization than before, we can clearly see how the smoke wraps around and spirals off the cylinder. There looks to be less separation as the flow coming off the top and bottom reconnects closer to the rear of the cylinder, creating a smaller low pressure zone. Looking at the coefficient of pressure plot, we see flow becomes turbulent around 40 degrees, right where the trip strip is, and then separates around 75 to 80 degrees. The cylinder plot shows how the vacuum pressure behind the cylinder is distinctly less than the previous run without a trip strip. Upping the wind tunnel RPM, we now reach a Reynolds number of 9.55 times 10 to the fourth. We see very similar vortex generation, only at a higher frequency. Flow quickly meets up behind the cylinder, limiting pressure drag. The coefficient of pressure plot reveals turbulence at the trip strip, and flow separation again around 75 to 80 degrees.
Here we compare the calculated coefficient of pressure values while using the trip strip at both 200 RPM, seen in blue, and 300 RPM, seen in green. The inviscid theoretical values, seen in red, are plotted again for comparison. This comparison exhibits many of the same trends as does the earlier comparison of 100 RPM versus 200 RPM without the trip strip. The striking difference here is that from a theta of about 40 degrees to 100 degrees, which is the area around the trip strip, we see the coefficient of pressure drop further for higher RPM/Reynolds numbers. This is due to the fact that at higher speeds, the trip strip creates more turbulence and thus keeps the flow attached for longer. Here we compare the coefficient of pressure profiles at 200 RPM both with the trip strip in blue and without the trip strip in green, while the inviscid theoretical values seen in red are plotted again for comparison. The difference between these two profiles happened mainly around the trip strip at a theta between 40 and 100 degrees. The coefficient of pressure profile for no trip strip in green matches the theoretical laminar profile, while the coefficient of pressure profile with the trip strip in blue matches the theoretical turbulent profile. In essence, when adding the trip strip, we can visibly see how intentionally tripping the boundary layer is a good mitigation to keep the flow from separating, as the turbulent profile correlates to the inviscid theory much more closely than does the laminar.
We were able to determine the effect of Reynolds number on pressure, drag, and their coefficients using variable fan speeds. This allowed us to determine the external forces our cylinder experienced when placed in the flow. These effects could be seen in the way the vortex shedding changed based on the various situations tested.
When finding error for the coefficient of pressure, we carried over the error from our pressure readings and average velocities. Then we propagated that error into the coefficient of drag calculation, as it is a discrete sum of the coefficient of pressure values. Having to use discrete pressure points around the cylinder instead of a continuous reading is simply one aspect which generated error. We tried to minimize error for this experiment by employing multiple sampling rates to see which rate would result in higher fidelity data. There are various other contributors to error within the lab, such as dropping the cylinder, doors being opened and shut while data was being taken, changing atmospheric conditions, incoming air being drawn through the vertical opening before turning horizontal down the tunnel, and people moving around the lab during testing. All of these contribute to the eventual errors seen in our coefficient of drag calculations, and why our calculations are slightly higher than the theoretical empirical data while still seeing the same trends. Finally, the error for the coefficient of drag is carried over into the final error calculation for the drag force on the cylinder.
We also verified a reduction in drag due to turbulent boundary layer effects through the use of the trip strip. This relates to strakes, which are used on real-life structures to break up vortices and diminish the frequency at which they shed. This is important because vortex shedding can cause catastrophic instability if the vortex shedding matches the harmonic mode of the structure, causing further excitation. It can be seen in the tripped flow that the turbulent boundary layer also had the effect of delaying flow separation, reducing drag on the cylinder. This is important as it would affect propellant efficiency in the case of an airplane, or increase stresses on any circular cylindrical structures within a flow.